Shapes of meniscus. We know that when the liquid surface it is in contact with the solid surface gets modified. This modified shape of the liquid surface it is called as meniscus. Here we will consider the different shapes of the meniscus. The first, concave shape. Consider the kerosene in the glass bottle. Here kerosene weighs the glass. And angle of contact theta, it is the acute angle of contact, that is less than 90 degree. Now, the liquid molecule, that is the kerosene molecule A, is in contact with the solid surface. This molecule A experiences two types of the forces. The force of adhesion between the liquid molecule A and the solid molecules. This force is along AP bar. It is perpendicular to the wall of the tube, or it is in horizontal direction. The second force, it is the cohesive force between the liquid molecule A and other liquid molecules. It is along AC, making an angle of 45 degrees with the wall of the tube or with the free surface of the liquid. Here, the AP, that is the adhesion force, is greater than the cohesive force. This AP bar is greater than AC bar. As this AP bar is greater than AC bar, the resultant of these two forces by the law of parallelogram of forces, that is AR, it will be outside the liquid. It is directed into the solid. Therefore, the liquid molecules like A, which are in contact with the solid, experiences this outward force. Now, to remain the liquid surface in equilibrium, it always tries to remain perpendicular to the resultant arc. This liquid surface, to remain in equilibrium, it always tries to remain perpendicular to this resultant arc. That is, the tangent drawn to the liquid surface, this AT and the resultant force AR should be perpendicular to each other, should be normal to each other. To make this, the liquid molecules which are in contact with the solid moves in upward direction, creeps in upward direction, piles against the solid surface, pile up against the solid surface, and therefore the liquid molecules which moves in upward direction and the liquid surface near the solid surface takes the concave shape. These molecules which are in contact with the solid, which are in the sphere of influence of the A, experiences forces in upward direction. This experience more force, therefore it will rise more. This experience less force, therefore it will rise less. It experience more less force, therefore it will rise. Therefore it will drop, then it will the concave shape. This liquid will take the concave shape. Therefore, here the shape of liquid surface in contact with the solid surface is concave. If we draw the tangent to the liquid surface, this AP and this, then the angle between this tangent and the solid surface lying inside the liquid, it is less than 90 degrees. That is, it is acute angle of contact. आपण विहीर असेल, आड असेल, त्याच्यातून हातावरून पाणी काढतो. बादली आडात असते, दोर आपल्या हातात असतो, दोरावर आपण फोर्स लावतो. हे फोर्स कसं राहतं, आडच्या दिशेत राहतं आणि बादली कुठे येते, वर येते. तसे लिक्विड मॉलिक्युल वर हे फोर्स ऍक्ट होतं अपवर्ड डायरेक्शन मध्ये आणि बादलीप्रमाणे लिक्विड मॉलिक्युल्स वरच्या दिशेने काय होतात, मूव्ह होतात. सॉलिडच्या कॉन्टॅक्ट मध्ये लिक्विड मॉलिक्युल्स मूव्ह होतात आणि इथला शेप असेल लिक्विडचा, तो शेप असेल, तो शेप कसा राहणार, असा कॉन्केव शेप असेल, तो कॉन्केव शेप काय करतील, ते ऍक्वायर करतील. सेकंड केस, convex shape. Consider mercury in the glass bottle. Now, the mercury molecule A, which is in contact with the glass, similarly experiences two forces. That is the force of adhesion between the mercury molecule, that is the liquid molecule, and other solid molecules. this force will be along AP, that is perpendicular to the wall, or it is in horizontal direction. The second force, that is the cohesive force, then between A and other mercury molecules, liquid molecules, it is along AC, making an angle of 45, nearly 45 degrees with the wall of the tube or with the free surface of the liquid. Now here, this AP additive force, it is less than the cohesive force. As the cohesive force is more, the resultant of these two forces AP and AC, that is AR, it will be inside the liquid, into the liquid. It is directed into the liquid. Now, to remain this liquid in equilibrium, it always tries to remain perpendicular to this resultant R. That is, the tangent drawn to the liquid surface AT and this resultant AR should be normal perpendicular to each other. Therefore, the liquid molecules like A, that is, which are in contact with the solid, experiences downward force into the liquid. Therefore, they move in downward direction, and the liquid surface near the solid surface takes the convex shape. This A experiences more force and moves more in downward direction. This experiences less force, it moves less distance in downward direction. It experiences, this distance is large, it experiences again less force, and it moves less distance downward direction. And the shape will be this, like this, that is the convex shape. Here, the cohesive force is greater than this additive force, and liquid surface in contact with the solid surface, it is the convex shape. If we draw the tangent to the liquid surface, that is AT, and the solid surface lies inside the liquid, then this angle theta, it is greater than 90 degree, that is, it is obtuse angle of contact. For mercury and glass, the angle of contact is greater than 90 degree, and the meniscus is convex meniscus. Now, here the third case. If we take the pure water and glass, pure water in glass, then the liquid molecule, that is the molecule of pure water A, and experiences similar forces, that is, one force, it is the additive force AP, which is perpendicular to the wall of the tube. Now here, the liquid molecules are less in number, therefore the cohesive force between the A and other liquid molecules is very small compared to this additive force. Therefore, it can be neglected. Therefore, the resultant AR, it should be in the same direction as that of the additive force as that of the AP. This resultant force AR and additive force AP will be in the same direction. Therefore, to remain the liquid perpendicular to this resultant R, it takes the semicircular shape inside the liquid. That is, if we draw the tangent to this liquid surface, then this tangent will be along the solid surface. The angle between this tangent and the resultant, it is 90 degree. Hence, the liquid is near the solid has the shape of semicircular shape. The tangent and solid overlap with each other, therefore angle between them, theta, it is equal to 0. Here the angle of contact theta, it is equal to 0 degree. Now the fourth case, here consider the liquid molecule A, which is in contact with the solid. Here we have again two forces, that is the force of origin between A and solid molecules. It is along AP perpendicular to the wall of the tube. Second force, cohesive force between the liquid molecule A and other liquid molecules. Here this is along AC, making an exact angle of 45 degree with the wall of the tube or with the free surface of the liquid. Now here, if this AP, it is equal to AC divided by root 2, this AP, additive force, it is equal to 1 by root 2 of the cohesive force, then the resultant of these two forces lies around the wall of the tube. This arc will be directed in downward direction and it is around the wall of the tube. Therefore, to remain perpendicular to this resultant arc, liquid will be the plane and horizontal. Here we get the liquid meniscus as plane and horizontal. If we draw the tangent to this liquid surface, then this tangent will be along the liquid surface. The angle between this tangent AT and the solid surface, it is 90 degrees. That is, these two are perpendicular to each other. Hence, here we get 90 degree of angle of contact. Here we can consider silver as a solid and pure water as a liquid. Thus we have four meniscus. The first, it is the concave meniscus. It is here. It is the angle of contact. It is less than 90 degrees. It is of acute angle of contact. Here, liquid surface partially wets the solid surface. Second, we have convex meniscus. Here we have mercury and glass as an example. Here this cohesive force is greater than adhesive force. Here the angle of contact theta, it is greater than 90 degrees. That is the obtuse angle of contact. Here this liquid does not wet the solid surface. Third case, here the angle of contact theta, it is equal to 0. Here we can take the example of pure water and clean glass. Here the meniscus shape of liquid near the solid, it is semicircular, semi-spherical. Here the liquid completely wets the solid. And the fourth case, that is of the liquid surface is plane and horizontal. It is for pure water and clean silver as a solid. Here the condition is AP, that is the additive force AP, it is equal to cohesive force divided by root 2, that is AC divided by root 2. Here the angle of contact theta, it is equal to 90 degrees. Thus we can say that if this AP, it is greater than AC divided by root 2, the meniscus will be the concave. If this AP is less than AC divided by root 2, then meniscus will be convex. Thus, here we have in general four types of meniscus: concave, convex, semicircular, semi-spherical, and here it is plane and horizontal. Shapes of liquid drop. Consider the small quantity of the liquid. It is taken on the solid surface. The liquid will either form a drop or will spread over the solid surface. This formation of drop or spreading over the solid surface depends upon the surface tension of the liquid, depends upon the angle of contact theta of the liquid. Now consider the liquid placed on the solid surface. This case we have three interfaces. One liquid solid interface, second solid air interface, and third liquid air interface. This formation of drop or spreading over the solid surface also depends upon the force due to the surface tension for solid air interface and force due to the surface tension for liquid air interface. Now, let theta, it is the angle of contact for given solid liquid pair. T1, it is the force due to surface tension for solid liquid interface. T2, it is the force due to the surface tension for solid air interface. And T3, it is the force due to surface tension for liquid air interface. Now, we know that the forces due to the surface tension are along the tangent, are along the surface, are along the interface. Therefore, T1 will like this, T2 will like this, and T3 will be along the tangent to this liquid air interface. Now, this T3 can be resolved into two components. We know that the adjacent side, it is related to the cosine component of the angle, and opposite side it is related to the sine component of the angle. And this is adjacent side, the component of T3 along the horizontal direction, it is T3 cos theta, and component of T3 in vertical direction, it will be T3 sin theta. Therefore, this T3 resolved into two components, T3 cos theta along the horizontal direction and T3 sin theta, it is along the vertical direction. Now, this component T3 sin theta balances the weight of this liquid. The T3 sin theta balances the weight of liquid. Therefore, as this liquid drop, it is in equilibrium, we can say that total horizontal force towards the left and the total horizontal force towards the right are equal in magnitude, opposite in direction. They are balancing each other. Therefore, we can write T2. It is the total horizontal force towards the right, and T1 plus T3 cos theta. It is the total horizontal force towards the right. Towards the left. Therefore, we have equation T2, it is equal to T1 plus T3 cos theta. We can write this T3 cos theta, it is equal to T2 minus T1, or cos theta, it is equal to T2 minus T1 divided by T3. We have equation cos theta, it is equal to T2 minus T1 divided by T3. Using this equation, we can discuss the different shapes of the liquid drop. We have equation cos theta, it is equal to T2 minus T1 divided by T3. Now, the first case here, in this case, if this T2, it is greater than T1 and T2 minus T1, it is less than T3. This T2, it is greater than T1 and T2 minus T1, it is less than T3. As T2 is greater than T1, the numerator will be the positive. Again, this T2 minus T1, it is less than T3, then there will be the fraction. Therefore, we can say that this cos theta, it is positive. As cos theta is positive, therefore theta, it is less than 90 degree. Here the angle of contact, theta, it is less than 90 degree. It is the angle of contact. It is the acute angle of contact. Here the liquid will form the flattened shape. असा थोडासा पसरट असा लिक्विड ड्रॉप असेल तो लिक्विड ड्रॉप इथं काय होईल फॉर्म होईल. Here the angle of contact theta, it is less than 90 degree. Now we will consider the second case. Here T1 is greater than T2. T1, it is greater than T2. Therefore, and T1 minus T2, it is less than T3. As T1 is greater than T2, the numerator will be the negative. Therefore, here cos theta, it is negative. Therefore, theta, it is greater than 90 degree. Here the angle of contact theta, it is greater than 90 degree. It will be the obtuse angle of contact. Here the drop will assume the contracted shape. असा थोडासा संकुचित contracted shape असेल तो contracted shape इथे फॉर्म होईल. Example, mercury and glass surface. In this case, example, water or kerosene and glass surface. Again, we will discuss the another cases. The third case, here T2 minus T1, it is equal to T3. numerator it is equal to the denominator. Therefore, cos theta it is 1, theta it is equal to 0 degree. Cos theta it is equal to 1, theta it is equal to 0 degree. Here the angle of contact is 0 degree. Therefore, there will be no formation of drop. Liquid will spread over the solid surface. There is no formation of drop. The pure water on the glass surface, for which the angle of contact theta it is equal to 0 degree. We can consider the another case, that is the fourth case. Here, this T2 minus T1 numerator it is greater than denominator. T2 minus T1 is greater than denominator T3. Now, cos theta it is, as numerator is greater than denominator, then this value will be greater than 1. Therefore, cos theta it is greater than 1, which is impossible. In this case also, there will be no formation of drop and liquid will spread on the solid surface. We can consider one more case which is not in our book. In this case, we can consider this T2 it is equal to T1. T2 it is equal to T1. Therefore, T2 minus T1 it is equal to 0. Therefore, cos theta it is equal to 0 and theta it is equal to 90 degree. And here the angle of contact theta it is equal to 90 degree. In this case, there will be semi-spherical drop. T3 will be like this, T1 will be like this, and T2 will be like this. Here angle of contact theta it is equal to 90 degree. When we place the pure water drop on the silver plate, then the drop will assume this semi-spherical shape. This is the fifth case in which this T2 minus T1 it is equal to 0. Therefore, we have total in general 4 cases. The first case in which the cos theta is positive. In this case, the angle of contact theta it is acute. The liquid wet the solid surface. Second case, the cos theta is negative. Here the angle of contact theta is greater than 90 degree. Here the liquid does not wet the solid surface. Third case, theta it is equal to 0 degree. Here cos theta it is equal to 1. Then there is no formation of drop. And fourth case, numerator that is T2 minus T1 it is greater than denominator that is T3, which is impossible. We have no such angle for which the cosine is greater than 1. Cosine of any angle lies in between +1 -1. Therefore, which is impossible, and in this case there is no formation of drop. The liquid will spread over the factors affecting the angle of contact. Now, the angle of contact depends upon the nature of solid liquid pair. First, angle of contact depends upon the nature of solid and liquid. If one of these is changed, then angle of contact changes. We know that for pure water and glass surface, the angle of contact is 0. If we take ordinary water and glass, then angle of contact is 80 degree. If we take the mercury and glass, then angle of contact it is 140 degree. If we take pure water and silver as a solid, then angle of contact is 90 degree. If we change the liquid, that is the kerosene, and the solid surface is glass, then angle of contact is 26 degree. Therefore, we can say that angle of contact depends upon the nature of solid liquid pair. If one of these is changed, then angle of contact changes. Second, it depends upon the impurity. The impurity present will change the angle of contact. And third, it depends upon the temperature. It depends upon the temperature. If the temperature increases, then the angle of contact decreases. For given solid liquid pair, the angle of contact remains constant at constant temperature. If temperature is constant, then for given solid liquid pair, the